Okay, we're going to talk about the SPK system now. This is, for many users, the sort of raison d'etre of Spice. It's probably unlike any Ephemeris system that you've used before, and we think you'll find it more capable. It's a little bit more complicated to grasp, but don't panic, you'll be reading SPKs like a pro shortly. So here's a very simplified view of Ephemeris data. We have examples of Ephemeris objects, and all the blue arrows in this diagram are position vectors. These arcs indicate paths, and you can see that the kinds of objects that we can represent ephemeres for are a variety of commonplace things, solar system objects, sun, Earth, so forth, but also spacecraft and components of spacecraft. Antenna feed cone is an example. Abstract objects such as barycenters are ephemeris objects, or can be considered to be ephemeris objects. There's the planetary system barycenter, center mass. Lander, you have an ephemeris for a lander as well. And there are reasons why it's convenient to do that, even though the lander is stationary. We use the term barycenter for the center of mass of a system of bodies such as Saturn, plus all of Saturn's satellites, or the sun and all the planets, satellites, comets, and asteroids of the solar system. An SPK file contains ephemeris, or synonymously trajectory data for ephemeris objects. And ephemeris, in our documentation, means position and velocity as a function of time. We refer to these two items collectively as state. So your state vector, we're talking about a 6 vector that consists of position and velocity. Ephemeris objects can be spacecraft, planets, satellites, comets, and asteroids, but also can include center mass of the solar system, center mass of the planet satellite system, rover on the surface of body, camera on top of the mast on the lander, transmitter, cone on a spacecraft, deep space communications antenna on the Earth, and in addition, components of artificial objects. So really, anything that you can represent a trajectory for can be an ephemeris object. Now, a single SPK file can contain data for multiple ephemeris objects, and it often does. Here's a simple representation of ephemeris data. It's just a time-tagged list of states. So we've got an epoch, followed by 3 position components in Cartesian coordinates, and then the corresponding velocities. And we have a time-tagged sequence of these state vectors. Now with this, there's actually quite a bit of missing information. It's not possible to interpret this without knowing what this is for, what reference frame it's in, and some other items. We need to know what is the center of motion. Without knowing that, we don't know where these positions are or what these velocities are relative to, what time system is being used for the epochs, and maybe also what are the start and stop times of the file. So what is epoch 1 and what is epoch n? So this is not really ready to use without additional information. So in the diagrams that are coming up, we'll use a block that looks like this one to represent a chunk of ephemeris data. This is the basis of a segment in an SPK file, and we'll talk about that more later, but SPK files contain one or more segments, and each segment is the ephemeris of some object relative to another object. So inside each segment, in addition to the raw data, we have some metadata that describes what the data are. Target, reference frame ID, center of motion, start time, and stop time. Those are all included with every segment. And so that makes it possible for software to know what object these data are for and what the center of motion is. So a simple SPK file might contain just one segment, and it has some other stuff. We mentioned that every binary Spice kernel has a common area. That's part of what this other stuff is. And then the segment with this metadata and the data. So this simple SPK file has ephemeris data just for a single object. in a given reference frame, having a single center motion with data spanning from t-start to t-stop. A more substantial SPK file can contain multiple segments. So we have here segments for a given target, reference frame, center motion, and a start time and stop time, and then another segment that covers a different time range. It goes from T3 to T4, T5 to T6, and so on. An even more substantial SPK file can have data for different targets and different centers of motion. And we see these different colored diagrams are supposed to suggest segments for different objects. So we've got different targets and different centers of motion. And in this case also we have different reference frames. And there are reasons why you want to use different reference frames. Some of the most common are you might want to use an inertial frame for some segments, and you might want to use a spacecraft fixed frame or maybe a topocentric frame for others. Okay. In addition to the metadata that we've described already, there's another piece of information in the metadata called the SPK data type. And here we're showing multiple data types all used in the same SPK file. Type 13, type 2, type 1. Every data type in an SPK file is an indication of the kind of mathematical representation used for the Ephemeris data. There are many types of data, even though we're showing here a time tag list of states. There are many possible representations. Here's one that uses Chebyshev polynomials. So instead of having this time tag list, we've got a sequence of sets of coefficients with a midpoint, radius. This is the midpoint of the time interval covered by a set of coefficients. The radius, that's the half the length of the time interval, and then a set of coefficients for x, y, and z. In type 2, this is a set of coefficients which can be differentiated to give velocity. So even though we have just polynomials for position, we actually have enough information in the segment to allow the SPI system to compute states. Here's yet another data type, type 1. This is what JPL uses for spacecraft ephemeres. This is modified divided difference arrays, also called difference lines. And that is a representation that is effectively a polynomial representation for acceleration with constants of integration. So we have an example of 3 different data types here. They're actually roughly, well, the data type numbers go up to 21, and there are I think, roughly 16 data types that are in use. Now that toolkit software knows how to evaluate each type. You don't actually have to you don't have to do anything different in your program to tell the SPK or SPICE what kind of data types are being used. You just load an SPK file, and the file is self-descriptive because it has this information in the segment metadata. And the SPK software will figure out how to evaluate the data that you've loaded. Important point, SPK data are continuous within the segments. You'll hear later about gaps within segments in C kernels, but in the SPK system, there can be gaps between segments, but segments themselves cover a continuous time interval. Within the time bounds of a segment, for example, T1 to T2 in this case, SPI software will return a state
That's on purpose, Nat, because it's really loud here in the back.
Okay. Can you hear me just fine without the mic?
No. Speak into the mic. We just reduce the volume a little bit.
Okay. All right. Is this good? This works?
Yes, it does.
Okay. Okay, so within the time bounds of the segment, SPICE will return a result, state vector consisting of position velocity at any epoch, not just the epochs of the Ephemeris records. You can see these time tags right here, but if you have a request time, you want to get a state for, say, the midpoint between epoch 1 and epoch 2, or in fact, any time between epoch 1 and epoch 2, SPICE will do an interpolation and return a state. So although we have discrete states in the file, SPICE Splice will behave as though this is a continuous representation. Next, we'll discuss chaining and frame transformations, features of the SPK system that make it rather unique. So Splice chains SPK data. Splice is capable of connecting information to compute state vectors for which you don't actually have raw data in any of the SPK files that you have loaded. Splice knows how to combine the data that you've got loaded to produce states that are computable, even though the individual SPK files don't support those states. But here we have a case where what we'd like to do is compute a vector. We'd like to compute the position of the Huygens probe sitting on the surface of Titan as seen from the Deep Space Station 14, the DSN Station 14. Now there is no SPK file that has, and you wouldn't expect there to be, the Huygens probe relative to DSS 14, but we can compute that using SPK files that are available. Okay, so here we've got a file for the Huygens probe. It's got Titan-centered positions in it, positions and velocity, of course velocity is 0. Well, that depends what time range it covers. It might, if this is for descent, then we would have non-zero velocities as well. We've got a Titan ephemeris. The Titan ephemeris has states of Titan relative to the Saturn barycenter. We've got an ephemeris for the Saturn barycenter. This is relative to the solar system barycenter. We also have ephemeris for the Earth barycenter relative to the solar system barycenter. The Earth relative to the Earth-Moon barycenter. The Deep Space Network station relative to the Earth. And with these states that do exist, that are provided by the SPK files, by the way, on the right-hand side here, we have labels for the SPK files themselves. Probe ephemeris file, DSN station file, satellite ephemeris file, and planet ephemeris file. So these state vectors are provided by the SPK files that we have available, and Splice will combine these. It can compute the state of the Huygens probe relative to the solar system barycenter. It can compute the state of the Deep Space Network station relative to the solar system barycenter. It can subtract this state from this state and give this final state. This happens all automatically. All you have to do is load these ephemeris, these SPK files, ask for the state you want, and Splice will do the rest. Now, in order to do the computation that I just described, Splice has to do reference frame transformations. Those SPK files don't all use the J2000 reference frame. It doesn't make sense to describe, for example, to describe the position of the Huygens probe on the surface of Titan in the J2000 frame. That needs to be described in the IU Titan frame, which is a body fixed frame that rotates with Titan. Similarly, for the Deep Space Network Station, we don't want to use an inertial frame. We want to describe the position of the Deep Space Network Station relative to the center of the Earth in a terrestrial frame that rotates with the Earth. So we've got a combination of segments contributed by these different files that use different reference frames. Here we have ICRF, IU Titan, ITRF 93 for the station, and topocentric frame. That's because we're using this frame because we're actually asking for, say, this is the user request. We're asking for the state in this topocentric frame. You might want to do that if, for example, we want to know the elevation of the position vector that points from the station to our target, which is the probe. So the segments we're using are labeled with these colors that indicate which frames these position and velocities are in. Blue for ICRF, this ochre color for ITRF 93, the purple color for Titan, the IU Titan frame, and the final vector is red, indicating this DSS 14 topocentric frame. Here's the SPK call. This is the Splice interface for getting state vectors, getting position vectors. There's a similar interface for state vectors. This gives you position only. This call says, return the state for the Huygens probe as seen from DSS 14 at the observation time t, which is barycentric dynamical time, seconds past J2000. Return the result in the DSS 14 _ topo frame and use converged Newtonian light time, and stellar aberration corrections. What are returned are the position and the one-way light time. So all of these state vectors from different files have been combined. The reference frame transformations have been done to allow valid addition and subtraction of vectors that originally were expressed in different reference frames, and the data were all combined. This one call does all that for you. So the user task is to load the right kernels and then write this call. That's it. Okay, observers and targets. This is unfortunate. The terminology that we use is a little bit confusing, and it is based on it's really biased toward remote sensing observations. There's the idea of an observer and a distant target. There are computations that SPK can do that don't really correspond to that model of what kind of position vector is being computed. So let's look at it in detail here. You get to specify which ephemeris object is the target and which is the observer. That's not necessarily what is literally the target and observer in your real-life computation. You can have a spacecraft be the observer, and it's looking at a target. And in this diagram, you're computing the position of the target relative to the observer. But this inanimate object can also be the observer, and the spacecraft can be the target. If you code your SPK call to model the geometry this way. Now, what really an observer is, it's the tail of the position vector, and the target is the head of the vector. Either way, the target's the head of the vector, and the observer is the tail of the vector. That is the relationship that's always true, regardless of what the physical roles of these ephemeris objects really are. So, sorry, it's a little confusing, but it is so well established historically that we are not going to change it anytime soon. SPK file coverage. There's a concept of coverage, meaning what are the set of bodies that are in an SPK file, and what is the set of times for which data are available for a given body. Here we're talking about time coverage. An SPK file is covered for an object, for a specific object, consists of one or more time intervals. Often the coverage for all objects in an SPK file is just a single common time interval. So this is a very common situation, particularly for planetary and satellite ephemerides, where all the objects in the file just have the same start time and stop time, and there are no coverage gaps at all. This is the most convenient kind of SPK file to use because you don't have to worry about data not being found. You can also have the situation where you have data for one object, but there are coverage gaps. So there are some intervals here between the intervals of coverage where there just simply are no data. You can have coverage which is different for different objects. In this example, we've got 3 objects, and we've got different coverage for each one of them. You could have a file where we have continuous coverage for objects, but the start and stop times don't all match up. And we can have data for several objects, each having the same coverage with no data gaps. So, sorry, actually, I misspoke. This is the diagram that refers to the planetary and satellite ephemeris case. This is just for a single object. Sorry about that. For a request time within any time interval comprising the coverage for an object, the system can return a vector representing the state of that object relative to the center of motion. So as we said before, the system will automatically interpolate ephemeris data to produce a Cartesian state vector at request time. To user's program, the ephemeris data appear to be continuous over each time interval, even if the data stored inside the SPK file are discrete. The SPK subsystem will not return a result for request time falling within a data gap. Gaps can only occur between segments. So results in this diagram, where these green bars represent coverage, for any request time within these coverage intervals, results will be returned, but not for request times in these gaps. And you might be wondering, does SPICE interpolate across the boundaries of segments? If you've got one segment that has a stop time, which exactly matches the start time of the next segment, Will SPICE interpolate across the boundary? The answer is always no. Time boundaries of segments inhibit interpolation, and there is never any interpolation across a gap. Okay, reference frames. So, as we've seen before, reference frames are included in the metadata for a segment. Identification of reference frames is essential to understand what state vector actually means. The frame specification is input by the SPK producer, and the input frame must be one known to the SPICE system. Well, a reference frame can be known to the SPICE system either because it's built in or because a frame kernel has been loaded that contains that specification. Now, program reading an SPK file specifies relative to what reference frame the output state or position vectors are to be given. You're not stuck with using the frame the SPK producer used. We already saw that in that chaining example where we asked for state vector in the DSS14 top-centric frame, and that is not a frame that is used in any SPK file. The output frame you select must be known to your program, so either it's hard-coded in SPICE or one specified in the frame's kernel. And depending on how the frame is defined, your program may need to have access to additional SPICE data in order to construct the specified frame. So for example, that frame might refer to C kernel data, it might refer to other SPK data. So all of the kernels needed to define the frame actually have to be loaded in order to use it. A little bit about barycenters. A barycenter is the center of mass of a system of bodies. For planets, it's the planet and the satellites that orbit the planet's barycenter. For example, for Jupiter itself and its satellites orbit the Jupiter system barycenter. When we say orbit, we don't mean that dynamically. We mean that's a center of motion in SPICE terminology. For the solar system, planet system barycenters are labeled 1 through 9 for Mercury through Pluto. Pluto, as we've said, is still treated as a planet in the SPICE system. Again, this is so built into our conventions that it's going to remain that way. And the Sun, it's body 10, they all orbit the solar system barycenter. And once again, that when we say orbit, we don't mean dynamically, we just mean that's the center of motion. Barycenter offset magnitude. Here's some examples of offsets between planet centers and planet system barycenters, and also for the Sun. And so we see that at this particular time, these are, not at this particular time. Okay. Estimated maximum values over the time range 2000 to 2050. So we see that, for example, for the Sun, the barycenter can be well outside the Sun, almost 2 sun radii away. We've got 0 barycenter offsets for Mercury and Venus. They've got satellites. Here's the Earth barycenter can be a large fraction of the Earth's radius. For Mars, for a long time we treated the Mars barycenter offset as 0, but as you can see, we here now have this little 20 centimeter offset, which is now modeled in the latest Ephemeris, and so forth. So, to recap, a single SPK file can hold data for one ephemeris object or many ephemeris objects, and it's quite typical to have many ephemeris objects. The objects in an SPK file need not be of the same type. One might find data for spacecraft, some planets, and some satellites all in one file, split across multiple segments. So here's a few examples. Here's a planet ephemeris. We have the solar system barycenter. Now, the objects in blue are centers of motions. There's no ephemeris data present for these centers of motion. So in a planetary ephemeris, we have the other objects relative to this object, but there's no actual ephemeris for this object. Here we see the barycenters, we see Mercury, Venus, Earth and Moon also in here. Mars barycenter alone, until the more recent JPL planetary ephemerides, I believe going up to DE 421, we used to have 499 in here, but we don't anymore. So you actually need to get for working with Mars, you actually need to get a Mars satellite ephemeris to give you that little offset between Mars and the Mars barycenter. And then we have these outer planet barycenters and the Sun. For an asteroid ephemeris, we we have the sun and Ceres, and again, we don't have the ephemeris for the sun relative to the solar system barycenter. You would load a planetary ephemeris as well to get that state. Here's a merged example of a merged planet and satellite ephemeris, and we see we've got the Jupiter barycenter. Sorry, we don't have the Jupiter barycenter. That's treated as a center of motion. The Earth-Moon barycenter, Sun, Earth, various Jovian satellites, and Jupiter itself, all in this one SPK file. Here's a few examples of Flight Project SPK file contents. So here's the Ephemeris for the Cassini orbiter. We have Ephemeris are relative to the Saturn barycenter in this case. Cassini spacecraft relative to Saturn barycenter. No data for the barycenter itself. One object and multiple files. For the Huygens probe, again relative to the Saturn barycenter, and the probe ephemeris itself. Multiple objects. We have Earth, Saturn, Earth mass center, and Moon, all relative to the solar system barycenter. And then Saturnian satellites, all relative to the Saturn barycenter, and multiple satellite files with possibly different sets of objects, all relative to, we're not saying what it's relative to, presumably Saturn barycenter. Users program must load as many of these SPK files as needed to satisfy various requirements. Sometimes a project nav team combines several of these collections before releasing them, making the user's job easier. Okay, so we'll not go into any more detail on that. Possible SPK file time coverages for the previous example. In this case, we have here each bar represents a separate file. So we have simply one time interval for the planet ephemeris. For major satellites, we have 2 time intervals, 2 files, 2 time intervals. For the second set of satellites, we've got 3 files, 3 time intervals. For the orbiter, we have many files. We have overlap here. Presumably, we have some predicted ephemeris data, which is then overridden by reconstructed data. And for the probe, we have multiple files as well. Here's the timeline that shows the mission phases that correspond to these different files. This was not the Cassini scenario, but it is an illustration of some possibilities for ephemeris delivery on a planetary mission. Okay, so how do you actually get data from SPK files? Well, you're going to need to load kernels. You'll need to load at least one SPK file. And most of the time, you'll need to load a leap seconds kernel. It's actually possible to use Spice without loading the leap seconds kernel, but if you're starting with UTC time, you will need that leap seconds kernel in order to convert the UTC to ephemeris time, which is the independent variable of the SPK system. It's the time system of the independent variable of the SPK system. Okay, so this conversion is done outside of SPK. You have to do this conversion to get the inputs that are required by the SPK interfaces. Retrieving ephemeris data from an SPK file is usually called reading the file, but this is not very accurate because SPK reader software also performs interpolation, may chain together data from multiple sources, as we've seen, do frame transformations, and perform aberration correction. So a great deal more than just reading is going on, but for traditional reasons, we still talk about SPK readers. Same position vectors retrieved from an SPK file are Cartesian vectors of the form x, y, z, dx, dy, dz for a state vector, kilometers in kilometers per second. The seconds that are the units of time here are seconds of barycentric dynamical time, and just x, y, z in kilometers for a position vector. So, how do we actually make these calls? Suppose we want to do a simple computation with one target and one observer. Well, the first thing that we do is we load our files, load an SPK file using the routine furnish. We also use furnish for loading the leap seconds kernel. Spice will figure out what kind of kernel you're loading. And we're showing Fortran syntax here. I'm sure that all of the Python users will be able to make the mental transformation to Python syntax. Now, it's better to replace these calls with a single call to a furnished kernel or meta kernel containing the names of the kernel files to load rather than make these multiple calls. That gives you far less code to edit and makes it much simpler when you want to completely change the files or move your files around. Note that these furnish calls are typically done once per program execution. In most simple programs, you load the files at the beginning of the program and then you do your SPICE computations. More complicated programs might need to actually change the sets of files that are available, and then there would be multiple furnish calls and maybe calls to unload or k-clear in between. But for everything we're doing right now, we're just going to load the files at the beginning and not do anything further with them. Sometimes new users misinterpret this instruction and think that the files need to be loaded before every call to an SPK interface. That is not true. They just need to be loaded once. And of course, if you do load these files before every call to an SPK interface, your program will run quite slowly. Then, as many times as you need to, convert your input time to TDB if you're starting with UTC time strings, and then you make a call to the principal interface to get a state vector. SPK ECR is the name of the principal state vector computation interface. You see here are the arguments, which will become familiar to you shortly, are target, input time, reference frame, aberration correction, specification, observer, and the outputs are state and lifetime. Okay, the target and observer accepted by SPK ECR are character string names, but they also could be NAIF IDs in string format. So you could have single quote, 599 single quote for Jupyter, for example. And the target is, remember, the target is the head of the position vector and the observer is the tail of the vector. The position component points from the observer to the target, regardless of the physical role, regardless of whether the observer is physically observing or not. TDB is the time at which the observer's location at which the state vector is to be computed. Yeah. So the time system is ephemeris time, barycentric, equivalently barycentric dynamical time, and this time is not necessarily the time of participation of the target. If aberration corrections are not used, the two times are the same. If reception aberration corrections are used, the time at the target is going to be earlier than this input time because it will be the state of the position of the target will be that at the time that it emitted photons, which will be sometime before the observation time. And if we're doing transmission corrections, the time at the target will be later than this TDB time. So this time is always associated with the observer. The frame is a SPICE name for the reference frame in which the output state vector is to be given. So this doesn't necessarily have anything to do with the frames that are used in the SPK files you're using. This is the frame that you want your output state vector to be in. Aberration correction, okay? This is a specification of what kind of aberration corrections to apply. Use LT plus S to obtain apparent state of target as seen by the observer. In the reception case, where the observer is literally receiving photons at time ET, when they're emitted at some earlier time, ET minus LT. CN plus S is better in some cases. The difference between LT plus S and CN plus S, or just LT alone and CN alone, is CN invokes the converged Newtonian aberration correction. That is a more accurate aberration correction estimate. And there are some cases where it makes a difference. Many times it makes no difference. Like if, for example, you are observing Mars or Mars orbiter from Earth, you will see in some cases that a significant difference in range is computed depending on whether you use LT or CN. So those sorts of computations we recommend using CN. Now, with Web GeoCalc or with the SPICE interfaces, it's trivial to try both of these aberration corrections and just see what the difference is. Use none to obtain the uncorrected state. So, for example, if you want to get a state that's exactly as it was in an SPK file, say Mars orbiter relative to the center of Mars, exactly as the data are in the SPK file, you use none. That will do no aberration corrections. Now, see the header of the subroutine SPK ECR and the SPK required reading or fundamental concepts tutorial for more details. The header of the SPK ECR is very detailed. It talks about aberration corrections at length. If you're using SpicyPy, then you would go to the CSpice header, just follow the link, and you'll see all that detailed documentation. The outputs are state vector. As we've said, this is a Cartesian state vector you requested. It has 6 components, 3 for position, 3 for velocity. These are of the target with respect to the observer, so that this is the first argument, and this is the 5th argument. The position component of the state vector points from the observer to target, and the velocity component of the state is just the derivative with respect to the barycentric dynamical time of that position. Lifetime is a one-way lifetime between the position of the target and geometric position of the observer at the specified epoch. And that's it. Okay, here's some examples with specific inputs. Here, we're computing the state of Titan, as seen from the Cassini spacecraft at the UTC epoch, this particular epoch. And the state vector is returned in the J2000 frame and has been corrected for both lifetime and stellar aberration. So we start out off with loading the kernels, call furnish, load the kernels we need. Again, it's better to put these, just list these in a metakernel, load that one metakernel. Take your input time, convert it from UTC time string, if that's what you're starting with, to barycentric dynamical time, which is this numeric representation of the time as seconds past J2000 TeV. And then you make your call with the target, your observation time, the frame, your aberration correction specification, your observer, and you get back the state in light time, and the state will be in this requested frame. Then you go ahead and do whatever computations you need to with these outputs. Often, SPICE subroutines will prove quite useful for that. SPK pause is the position-only analog of SPK ECR. That was the first SPK interface we showed. The input arguments are identical to those of SPK ECR, but the outputs are a little different. SPK pause returns only a 3-component position vector instead of a 6-component state vector. It executes more quickly than SPK ECR when stellar aberration corrections are used. That's because it takes a fair amount of time to compute the rate of change of stellar aberration. SPICE has to actually estimate the acceleration of the observer for that. So if you don't need velocity and you are doing aberration corrections, it can be quicker to call SPK pause. SPK pause also can be used when reference frame transformations of velocity are not possible due to the absence of C-kernel angular velocity data. There are cases when you just don't have the data you need to compute a state vector, but you can still compute a position vector. Now, if you are starting with an SPK file, SPK files always do have velocity information, but if the output frame that you're using is one that requires C-kernel data to transform from the frame in the SPK file to the output frame you want, that C-kernel data might not be available. But so even though the velocity are available in the SPK file, you can't get that velocity out in the frame that you want. But SPK pause doesn't have that problem. It's not trying to compute velocity. Okay, here's a slightly more complex example. We can get state vectors referenced to a non-inertial frame, or we can do computation when the data within the SPK file are provided in a non-inertial frame. And we'll typically need more kernels to do that. So we're probably going to do a transformation from that non-inertial frame either to an inertial frame or yet some other non-inertial frame. So to get the state of an object relative to a body in the body's IU body fixed reference frame, you'll need a PCK file containing orientation data for the body, SPKs for the object and body, and a leap seconds kernel, most likely. To get the state of an object in a spacecraft fixed reference frame, you'll normally need frame kernel, C kernel, and S clock kernel for the spacecraft, SPKs for spacecraft and object, and leap seconds kernel. Here's a specific example. We're going to compute the state of Titan relative to Cassini, but this time we're doing it in this body fixed IAU Titan frame. This is the frame we want our outputs in. So we'll load the kernels that we need. notice that we're loading, in addition to our SPK file, we're loading and LeapSide's kernel, which we're loading already. We're now loading a PCK. This is going to give us the data that are needed to describe the orientation of Titan as a function of time. All this information needs to be loaded, yet again, list those files in the furnished kernel, meta kernel. So we do this once at the beginning of program execution, and then as many times as we need to, we call string to ET to convert a UTC input time to TDB. That is, if we are starting from this, that's not always the case. And then we make our call to SPK-ECR to get our state vectors. So here we have our target, our time, our frame, aberration correction, our observer, and we get back state and one-way light time. And at this point, we would normally have additional code to do some computations with these outputs that we've just obtained. Okay, there are a lot of tools in Spice for manipulating SPK files. You can subset an SPK or merge two or more SPKs. Subset or merge can be keyed off of objects, time, or both. You can merge only portions in SPKs. In many cases, an SPK file might have a lot more data than you really want, and you don't want to have a 500 megabyte file or 1.5 gigabyte file. So you can use SPK merge to cut down the file to what you need. That can be quite helpful. There are other reasons to do merge as well. But one should keep in mind that SPK merge actually is not just a merge program, but a subsetter as well. And more generally, it can merge subsets of specified files. You can read data from just one or many SPK files in your application program. We didn't actually yet show an example where you're loading multiple SPK files, but that would normally be the case if you want to load, for example, both satellite and planetary ephemeris and maybe a separate spacecraft ephemeris. Don't forget the precedence rule. That in a later loaded file, take precedence over data from an earlier loaded file. So we've mentioned this concept of precedence. If we have data that are competing, and the data that you want to have highest priority should be the data that are loaded last in the meta kernel. So that is, if you list it last in the meta kernel, if you want it to be loaded last. And if you want it to have highest priority, you do want it loaded last. You can convert an SPK that's in non-native binary format to native binary format if you need to add data or comments. So we haven't talked about that much, but it has been mentioned, you can't write to a non-native binary SPK file, although you can read one. If you need to add comments or add data, those are modifications to the file, and the file must be in native binary format. Spice has tools for doing those conversions to get the file into native format. By the way, the allowed number of simultaneously loaded DAF and DAS-based files, and SPK is a DAF-based file, is set to 5,000 in the N66 toolkits. Now, the actual number of files that you can load is typically smaller than 5,000 because you're going to normally load files other than SPK into the DAF system. And also, the efficiency of the DAF system is somewhat lower when you have that many files loaded. In any case, that is a hard limit for the DAF system. SPK producers should have provided descriptive data, metadata, inside the SPK file in the comment area. Comment should say when, why, how, and for what purpose the file was made. Additional useful information can be provided by the producer. Example, when and why any data gaps are present. I have to say that in my own work, I normally just don't use a file that doesn't have comments. If the file doesn't have comments, unless it's a very local situation, I'm going to assume that the file is completely unsuitable because I can't describe to any customer what I've computed. We need these comments, these descriptive comments, in order for the data to really be meaningful. Comments can be extracted using the API subroutine or viewed using a Spice utility program. DAF-EC for extract comments is an interface routine you can use to extract comments in the text buffer. And the utility program comment is really the most frequently used. If comment is in your path, if all the Spice executables are in your path, then you can just type comment and then -r and then the file name, and you will see a display of the comments in the SPK file. There are a bunch of utility programs that support SPK manipulation or observation, inspection, brief, summarizing coverage, space it for generating a segment-by-segment summary of an SPK file, comment for reading, appending, or deleting comments, make SPK for converting ephemeris data provided in a text file into an SPK file. SPK diff compares to SPK files, and it can be used to actually do a data dump based on samples from an SPK file. So this can be a quick way to just extract your own set of time-tagged states from an SPK file. SPK merge subsets in SPK merges or can merge pieces of SPK files. There are additional SPK utility programs that are not part of the SPICE toolkit, but you can get from the SPICE server, the NAIF website right here. SPI is a much more heavy-duty program for validating, inspecting, and analyzing SPK files. SPI allows you to see the exact contents of an SPK file, literally down to the bit level. Pinpoint creates an SPK file for fixed locations. If you need to create an SPK file for a ground station, Pinpoint is the tool for that. The SPID mod alters body IDs in an SPK file. This should be done very cautiously. Obviously, you're changing the IDs from what the original creator put in the file. You may be giving rise to a lot of confusion if you're sharing that file. The same goes for DAF mod, it alters body or frame IDs in an SPK file. DAFCAP concatenates together SPK files. So this is really a very low-level version of SPK merge. This just slams the data together, doesn't have any subsetting capability at all. And it actually concatenates segments from DAF files. I believe it does have error checking to make sure that you're not concatenating segments from SPK and CK together. Worse? That got smart enough to check the file type.
Yes.
Yeah.
Yes.
BFF displays the binary file format, so that'll tell you whether you've got a big endian or a little endian file. And Bingo converts SPK files between big and little endian formats. This is the most convenient utility to use if you've got either a big endian file which you need to convert to little endian or vice versa. For summarizing an SPK file, brief is the most convenient utility to use. You simply, in the simplest way of invoking it is simply to type brief in the name of the file that you want to summarize. And this is what the summary looks like. In this case, we've got a file where we've got multiple objects in the file, and they all have the same start and stop time of their coverage. So we just see this one time interval for all these objects. Note that, by default, the time system is ET barocentric dynamical time. And we have to be careful when we're trying to understand the data availability. The stop time here is, well, both these times are in ET, and since ET runs ahead of UTC, if you are looking for data that's on at 2000 May 1st, 9:34:03 UTC, well, that time is actually later than the time that's in this file. By the time that UTC gets to this value, ET will be some later time. So you'll not have data. So pay attention to this. It doesn't matter what time system you have. ET and UTC are more than 1 minute apart, and you can run into problems if you're assuming that you've got UTC in these outputs. Okay, for summarizing a file, use the -C option to show the center of motion for each object. So with this -C, we now see all the centers of motion for each object. We have this with respect to, and then for each object we have the center of motion. For more information, we have the online SPK tutorial. Most useful routines document shows you other APIs that we haven't discussed here. In particular, the ones for constant position and velocity targeted constant position and velocity observer are quite useful. And we haven't covered those. Also, the SPK coverage routines, SPK obj and SPK cov. SPK required reading document describes all of the data types in particular. Headers of the subroutines, using frames tutorial, which I'll show later, and the brief and SPK users guides. Also, A5D's required reading gives you all the details on A5D. Frames required reading describes frames in much more detail. And we have time required reading, which describes the time conversion routines that are available. Kernel required reading for the format of kernels, format of text kernels, which can be useful if you are looking at meta kernel to indicate the files you want to load. Okay.